Okay, minasan, konnichiwa, Zamurai Engineer desu. So, in this video, let us take the last topic for this course, a very short description of beam as a structural element. So this time we are going to use the steel principle. So before that, please sound check. So clear po sir, according to Joe. So shout out sa'yo. Therefore, let us proceed. So, beam as a structural element is, as we know it, for several courses already, several topics, we know that they are flexural elements. Right? So flexure, let us therefore present to you the theory behind this flexural element. So let us move on first to flexural element of beam with regards to yielding and plastic moment. So there are three strength, yield strength, lateral torsional buckling, local buckling. So that we will take a look into this particular element with regards to flexure. So we might be able to look into the shear strength and serviceability topic. But anyway, we'll focus on the very basic concept and introduce to you the most important theory, concept, and principle, and couple it, complement it with the code provision and manual. Okay, so let us proceed. So a beam structure is like this one. So there are one or two support at the ends, and technically a beam is a member subjected to bending or flexure and shear, and because of that you can see the shear force and moment being applied to the element. Okay. Yield and plastic moment first. So let us separate the shear discussion. So first, for bending. So let's take a look at the bending side of things, wherein it will become a failure according to yield and plasticity. Yield and plastic moments can be related to stresses. Okay, so rho, strain, epsilon, and curvature, angle. Curvature is angle. Okay, so assumptions. So by the way, we already know this. Apply the theory of structure, rho, strain, and curvature. In here, theoretical discussion assumes the following: stress-strain law initially assumed linear, elastic, no residual stresses. Okay, when we are talking of elastic. So, ideal condition, straight line, then straight line. Straight, straight. Okay? Plane sections remain plane. Strain varies linearly over the height of the cross section for elastic and inelastic range. Okay? Then we have the following diagram for strain and stress. Stress strain diagram. So still again, we already know this. Just to review, E is the modulus of elasticity. ESH is the strengthening, okay, modulus. Okay, so this is the what? Strengthening portion. So yield, again ultimate. And for the strain, we have epsilon U, epsilon R. R is for rupture. Okay. So E epsilon is strain hardening. So strain hardening. So again, what happened? So for the ideal, just like what I've said, straight line, it's straight line. So there are two straight lines here. Going up with a slope of E and then horizontal. Okay, so that is the ideal condition. So using therefore the magnitude Fy as our main value. Okay. Then initially we will review behavior in this range, okay, elastic region. Then yield in plastic moment will look like this. Okay. So plane sections remain plane. So as you can see on the cross-sectional area, there's no distortion or there's no change of cross-sectional. That is an assumption. That is not a reality. So to be able for us to analyze, simply relate to the graph and so on. Then later on, as you become an expert, you will now introduce modification, okay? So that you will go improve your estimate near the actual value. Okay? So again, forces equal summation of forces, okay, integral of rho delta A. So just multiply every stress for the corresponding area, then sum them all. It would be equal to 0 in total. Okay, 0 because we are in equilibrium. Okay, so reactions will cancel out with the initiating force. Okay, so force will cancel out for every reaction, so they will all cancel out into 0. Okay, so for Fi, meaning for every element, for every one, then small amount here, small part or small region, small element. No? So delta area or a small delta area multiplied by that stress in that point. So we'll have Fi. And then summation of that, so it's equal to 0. And then for the moment, just multiply this force by Y, meaning this is the moment arm, and that is supposed to be integral of y rho delta A. So where y is the centroid of that particular area of concern. Okay? So if you are going to do it on infinitesimal area, so instead of integral, summation y f I. Okay? So yield and plastic moments continue. So for every free body diagram, so we have reaction and the action and reaction. Okay, so they will just cancel out. Then we have the usual, the most common section, cross-sectional area. So we have the neutral axis in the middle. So from the middle, from the neutral axis going up, that is usually the tension side. From the middle going down, that is usually the compression side. So as you can see, straight line relationship, okay, represents strain, and also a straight line relationship represents the stress with regards to a specific location with respect to neutral axis. So as you go away from the neutral axis, the stronger the particle on that portion will feel the load, and also the longer the strain will be felt at that location. Okay. So the closer is the particle to the neutral axis, the smaller the strain and corresponding stress would be felt. Okay. So elastic behavior, strain related to stress by modulus of elasticity, and this relationship. Notice this is the independent variable, this is the this dependent variable, independent variable. This is just what? Y is equal to E of A times X. Equation of a line. This is just equation of line. Okay? Wherein E is the what? Y is equal to mx. M is the slope. So M is equal to E. So that is the slope. Okay, so again, same diagram, but now consider what happens once some of the steel yields. Okay, what happened? The steel yields, some portion of the steel yields, what will happen? Okay, so what? Beyond yield, stress is constant. Okay. Here, okay. Strain is not related to stress by modulus of elasticity anymore, because here, there's no relationship. Okay. Increasing strain, but our stress is now constant. And we have the following. So the cross section, okay, again, the farther away from the neutral axis, the larger the strain. Similar is true with the stress, the farther away, that is. But when we are moving beyond elastic behavior, so this is elastic, but now when we are moving to the plastic region. This is now plastic region here, plastic region. So as you can see, some of the components will experience the maximum stress. This is the maximum stress, or FY already. This, and we cannot have more than FY. Okay? So that's why it is now truncated. The straight line model or representation or the relationship is now truncated here to the amount equal to FY. Okay? So, and then if you increase further the load, so it will look like this, meaning the region which is still elastic will what? Lower and lower its what? Or increase its slope. Okay? Increasing slope up to the point wherein it is straight lines, is horizontal. Okay? Okay? Theoretically reach the infinite strain at this point. Okay? So that will happen, as you can see. We can analyze it using different area for plans A1, then upper part A2, lower part A2, and then plans lower part. Okay, so we have elastic neutral axis is the centroid. Plastic neutral axis, we don't know. If homogeneous material, similar Y. PNA here, that is the plastic neutral axis, PNA, so elastic neutral axis. Okay, divides equal areas A1 plus A2 over 2. So neutral axis may move. Depending upon the balance between tension and compression part in the cross-sectional area. For a symmetric homogeneous section, PNA is just the same with ENA, which is the neutral or the centroid. Okay, so we have the section modulus I over C. Okay, section modulus is I over C. Okay, so I is meter or mm to the fourth power. C is in meter or mm, so therefore the unit of section modulus S is meter to the third power or mm to the third power. So the same is true with the section modulus here. So Z is the section modulus in plastic section modulus. This is S. This is elastic section modulus. Notice C is the distance to the outermost fiber. Okay, that is C. Okay. Take note, for homogeneous material, Zx is just the summation of A and multiplied by Y. Okay? Just the summation. Section modulus. And moment of inertia, as we already used this time and again. So This is BH cube over 12 plus A y squared. So A is the area, then centroid squared. Okay. Or distance squared. So we can also have the property shape factor, which is moment in plastic divided by moment in elastic. So we have the shape factor. So you can see here, my is the denominator, mp zxfy. So sxfy zxfy, the same formula, but now we are having plastic section modulus. So for for as you can see here, you can compare. Now as you can see, the green portion is still on the plans, so NA divides equal forces in compression and tension. Okay, a possible grade of steel, PNA divides equal areas. That is a concept, and that is a logical use of mathematics and science. Okay. So we have therefore just multiply every small component, then summation, or we can have the total section modulus. So with the residual stresses, first yield actually occurs before my. So because we have residual stresses, so the residual stresses will contribute to the total. That's why my will be less. Okay, because of that residual stress. So how can we develop that concept? So therefore, all first yield equation in the specification reference, so we'll have what, 0.7 FYSX. Okay, this indicates per shield 30% earlier than my. For 50 KSI steel, this indicates an expected residual stress of 50 times 0.3, that is 15 KSI. That is the residual contribution, right? So then consider what this does to the moment curvature relationship. So as you can see, my is a little bit, so 30% lower. So this is our my. This is our MP. Okay, so now if you are looking at moment versus curvature, so we have EI instead of E. The slope is EI instead of E. So because if you divide this by I, we'll have what? We will have the stress. Then this one divided by I, will have the strain. So consider this is now the further increase of residual stress. So as you further increase, the lower the curve will become. So for example, this is 1, and we have another 2, another curve here. So an increase in residual stress will make this curve lower. Okay. So that's the concept. That's the conceptual discussion of yield. So any question about beam section when we are talking about yield and plastic moments? Okay. Then there are no questions. Let's go to the next, the torsional buckling. Okay, let's go to the torsional buckling or lateral torsional buckling or LTB. Okay. So lateral torsional buckling. So LTB occurs along the length of the section. Okay. Along the length. So we are assuming it is present in each of the cross section. Compression flange tries to buckle as a column. Tension flange tries to stay in place. So because it is a beam, so there is a portion with tensional influence, and there is a portion with compression influence. So result is a lateral movement of the compression flange and torsional twist of the cross section because of this. So this is the reason. Because compression always tries to buckle as a column, while tension flange tries to stay in place. So that's why we tackle compression, we'll tackle buckling, global buckling, local buckling when we are under the compression members, but not when we are discussing tension members. So these are the flange reaction. So compression flange, usually this is on the upper flange, the top flange, and then lower flange tension. Okay. And we have again, for example, so X denote lateral brace points. So there are bracing here. So there are how many bracing? 1, 2, 3, 4. So there are 4 here. So this is LB. So LB now is what we call as unbraced length. So not the support length, but the bracing. Okay, pitch of bracing. So lateral torsional buckling, factors, and LTB. Strength. So length between the beam lateral bracing points. CB, very important. Also, measure of how much of the flange is at full compression within LB. And FY and residual stress per yield. So model of per yield. That is what we mean by per yield. Okay, per yield model. Just like on the previous topic. So per yield meaning first order model. Beam section properties, again, we have J, CW, RY, SX is ZX. So, what do we mean by those things? So, following section have inherent restraint against LTB. Okay. So, what are those? Typical shapes and sizes. W section. About its minor axis. Okay. Minor axis. So, it could easily buckle in torsion. Back section about either axis. HSS section about any axis. So, these are the most susceptible configuration. So, for these cases, lateral torsional buckling typically does not occur. So, if does not occur here, so those at risk are not listed here. Okay. As an example, what is that? So, major axis. So, it could buckle torsionally, major axis, because it is longer. That's why it could easily buckle rather than minor axis. So that is the susceptibility for occurring. No? So that's for the second type of failure mode. Okay, any question? That is the concept. So we are now able to discuss two concepts: yield, buckling, and this one is lateral torsional buckling or LTB. So now there are still no question. So let us now proceed to what the code suggests. Okay, what the code suggests for all of this. So let us $90. Let us increase this to 90. Okay, so here again the same courtesy have to be given to IIEC, particularly the developer of these modules, Professor Sibjan. Now let us now talk about the suggestion of the manual or the code, okay, with regards to beam members. So let us proceed. So flexural strength. The following slide assumes compact section, doubly symmetric members and channels, major axis bending. Flexure is beam. So first we are talking about flexure. That's why let's talk about this first. So when members are compact, only consider LTB as a potential failure mode prior to reaching the plastic moment. Okay. LTB, if the members are compact. Okay. according to the code. LTB depends on unbraced length, LB, and can occur in the elastic or inelastic range. Okay. And if the section is also fully braced against LTB, Mn is equal to Mp is equal to FyZx. Okay, this is the equation F2-1 from the code. Now, when LTB is a possible failure mode, so we have again the equation given MR, okay, rupture, moment of rupture, 0.7 FySx. We already talk about why it is 0.7, because there is a 30% stress, okay, and LP, okay, is equal to 1.76 Ry square root of E over Fy. That is the next equation. And then LR is equal to 1.95 RTS E over 0.7 Fy. So 0.7 Fy here. Square root of this value. What is this? JC over SHO plus square root of quantity JC SXHO squared plus 6.76 quantity 0.7 Fy over E squared. Okay. Another equation from the code. Notice the complicated formula involved here. What is RTS? RTS is equal to this. So RTS squared is equal to square root of IYCW over SX. So Ry is equal to square root of I over A. So this is just what? The y-axis radius of gyration. What about C? C is equal to 1. When here, C is equal to 1. Here. Okay, what about HO? This is the distance between flange centroid. Centroid to centroid. Distance. HO. So here, as you can see, HO. Okay, so this is the centroid to centroid distance of flange. So next we have lateral torsional buckling or LTB. Lateral brace, so you have what? Bracing. This is the location of bracing. Okay, that is what? Length or distance of between brace. Okay, so again, very familiar curve here, wherein we have what? Elastic region, we have inelastic, and then we have plastic. So inelastic is the region intermediate or in between elastic and plastic. Okay, a very small region here. So what is this? M is equal to constant, meaning C, B is equal to 1. So if you have M, constant. Okay. So if LB is equal to or less than LP, so Mn is equal to MP. If LP is less than LB is less than LR, okay. So we have the following equation for Mn is equal to CB quantity MP minus quantity MP minus 0.7 FySx times quantity LB minus LP over LR minus LP. This must be equal to or less than MP. Okay. Of course, it is usually MP which is higher or equal to Mn. Okay? So if LB is greater than LR, so Mn is equal to FCR SX. Okay, notice here, CR SX is equal to or less than MP. So where FCR is what? What is FCR? FCR is CB pi squared E over LB R TS squared. So this is the slenderness ratio. So slenderness ratio just multiply CB. This is just what? A modified Euler. Okay, this is a modified Euler formula. This is the modification and also CB. Okay. Assume CB is equal to 1 for now. So CB is equal to 1. So this is just the remaining modification. Composed of what? J, C, divided by SX, and so on. Okay? So plots of phi Mn versus LB for CB is equal to 1 are tabulated. Table 3-10. So results are included only for W section, typical for beam, Fy is equal to 50, CB is equal to 1. So that is a very basic type of tabulation, no? Table 3-10. So compute Mn for any moment diagram. Okay. And then Mn is equal to CB, quantity Mn CB1 must be equal or less than NB. So phi Mn, this is the design strength, design moment. Okay, design moment is equal to CB, quantity phi Mn CB1. Also must be equal to or less than phi MP. So M CB1 is equal to Mn, assuming CB1 is equal to 1. Okay? Okay? So it just depends on CB1 or CB. So what is CB? So you can compute CB in this formula. This is from the code, which is equal to 12.5 M max. So maximum moment divided by quantity 2.5 maximum moment plus 3 MA plus 4 MB plus 3 MC. Okay? So that is how to determine CB. It is a ratio. Okay? So shown is the section of the moment diagram between lateral forces. As you can see, LB over 4 and B over, so 1/4. Okay, so LB over 4 over 4. So from brace to brace, we divide them into 4 from brace to brace. So we have MA, M max, MC, MB. So A, B, and C. Okay, so we have maximum. So these are the relationship. Okay, so M max, absolute value of maximum in the unbraced section. MA, absolute value of moment at quarter point. MB, absolute value of moment at center line. MC, absolute moment at 3/4 point. So as you can see here, third quarter point, second quarter point, or at the middle, and the first quarter point. A, B, C. And then the value of maximum. Okay. So knowing those things, we can calculate CB. Okay. So after calculating CB, for example, considering a simple beam with different lateral brace, as given here, is the given example. We have the load. So X to X, just is the bracing. So we have this moment, okay? Because we have what? Concentrated load, that is the moment diagram. So if we have this additional bracing, okay, we have the following. Okay, so we can see M. So we can just cancel out M because we have the same value. So now B is what? 1/2. C is okay 3. Okay, so 4. So we have almost the same, no? So we only have 2 brace here, but here there are 3. We will have here 3 port, okay, 3 port, 1/2, 1 port. So 1 port, 2 port, 3 port, because there are 3 of them. Okay, that's why it's different values. Okay, next, so flexural strength again. So we have what? Moment diagram. So moment divide to moment. So therefore, this is 1/2. So going up, CB is 1.25. If this is the shape of the moment diagram, CB is equal to 1.37. And if this is the shape, CB is 2.3. So it depends. Okay? So this is a brace length maximum. So this is how you compute it. So, meaning to say, CB approximates an equivalent beam of constant moment. Okay. So now, it is now becoming apparent to us what effect CB will give us. So visually, it's better to see it visually rather than the formula of CB. It's very complicated. So we have 3 section: elastic region, inelastic, then plastic. So CB is equal to 1 here. MN. So what do we mean by MR? That is the rupture. Then MP is plastic. So next we have CB1. If CB is greater than 1, so the graph would become higher. Okay. So again, MP, MR, MN. So MN here. So MR, MP. So LP, LR, and then LB. So next, we have limited MP. So we have what? The model. So modeling straight, then go to the inelastic and elastic region. CB is greater than 1, higher. CB is equal to 1 is our lowest portion. Again, we have this as suggested and introduced by the code. Any question? Shout out Brian Oreta. Okay, so so napadaan si Brian. Okay. So let us proceed if there are no question. Now let's go back to the third. theory and manual. So we are through with the yield and plastic moment. Number 2, lateral torsion buckling or LTB. Now let's go to the third, which is local buckling. Let's go back to the local buckling. So what about the concept of local buckling? So for local buckling, we have the following concept. So it is related to plate buckling. So flange is restrained by the web at one edge. Okay, so we can have a local buckling here, but it is being restricted by this web. So what will happen? Partial restraint from the web. Okay, so failure is localized at areas of high stress or maximum moment or imperfection. So for example, this is the high stress area. So it will buckle this manner. So like this, it will buckle like this. Okay. Because of this too much stress here, how do we buckle? So that is buckling here. So it will yield and locally buckles like that, no? Partial buckling. So web is restrained by the flange. So we are taking a look at the local buckling related to plate buckling. So we have what? Partial restraint from the flange. So meaning now the web is the weakest portion, then it is being restrained by the flange, but still it will buckle. How it will buckle? So like this, it will receive too much pressure and more than its yield point, then it will buckle like this. So the web will buckle like this, okay, locally. So it will not be felt throughout the length, but it is only on a specific portion. Okay. So if a web buckle, this is not necessarily a final failure mode for web buckling. Okay. A significant post-buckling strength of the intersection may be possible. So that is for web buckling, particularly local web buckling. Not yet. We can still use the structure. One can conceptually visualize that a cross-section could be analyzed as if the buckled portion of the web is missing. So we can still analyze. Okay? Analysis part. We are not going to design it this way, but we can analyze it this way. But if you can imagine, there are W section with web which are perforated. So that is analyzed that way. Perforated. So it looks like perforated. Okay. The only difference that is here you have to expect that the buckling is on the compression side. As the concept suggests, there's no buckling on the tension. So this tension side, there's no buckling. So only on the compression side, there is a hole. But if you are using perforated type of web, it is not material, doesn't have any meaning whether you are in tension or compression. It is according to the design, perforation design. Okay. So local web buckling concerns. So bending in the plane of web, it reduces the ability of the web to carry its share of the bending moment. Okay, even in elastic range, there is a portion, there is some percentage that the web participates in resisting the load. Okay. Support in vertical plane. Vertical stiffness of the web may be compromised to resist compression plans downward motion. Okay. Then, shear buckling, shear strength may be reduced. Okay, so those are for our third type of failure mode, that is local buckling. Now, let's go to the corresponding code requirements. So, for the code requirements, so let us search for the code requirements for local buckling. Okay, so local buckling. So we have criteria in table B for this one. So we already know this table. Strength in chapter F, which is flexion. Strength in chapter G, which is shear. Let us proceed. Therefore, for this type of flexural strength, local buckling criteria. Slenderness of the flange and web, lambda are used as criteria to determine whether buckling would control in the elastic or inelastic range. Otherwise, the plastic moment can be obtained before local buckling course. So, criteria lambda P and lambda R are based on plate buckling theory. Plate type of buckling. Okay. For example, W shape, so we have the following. For W shape, we have FLB, lambda is equal to BF over 2 TF. So, lambda PF is equal to 0.30 square root of B over Pi. Lambda RF is equal to 1 square root of B over Pi. Okay. So, for WLB, okay, lambda is equal to H over TW. Okay, so lambda PW is equal to 3.76 square root of B over Fy. Lambda RW is equal to 5.7. So there are several things that we need to be aware of. I do not recommend to memorize this, but you should be aware of. These things. Okay. There is a concept like this one. Okay. Even for W shape. So we have plans, we have web. So this is for plans and for web. Okay. So local buckling, compact section. What do you mean by compact section? Lambda is equal to or less than lambda P. Okay. So MP is reached and maintained before local buckling. So meaning to say phi MN is equal to phi MP. That is what we mean by compact. That is the definition of compact. So non-compact. So lambda is greater than lambda P but less than lambda R. So local buckling occurs in the inelastic range. Okay. So we are now in the inelastic range. So this is number one, this is in the plastic region. This is inelastic region. This is in the elastic range. Okay. Because lambda is greater than lambda rupture. Okay. Lambda rupture is less than lambda. So therefore slender element. So that is what we mean by our classification. So compact, non-compact, and slender. So if you can take a look at the diagram again. take note of 0.7 my, right? 0.7. So this only means this way. This is what? Non-compact. This is compact. This is slender. Slender, non-compact. This is compact. Everything here, this is compact. So if the computation revolves around this, so this is compact section. Therefore, rolled W-shaped sections are dimensioned such that the webs are compact and plans are compact in most cases. Therefore, the full plastic moment usually can be obtained prior to local buckling occurring. So this is I think the safest, no? Okay. So meaning the possibility of buckling almost very low, very low possibility of buckling. That is what we mean by this. Okay, because it will go to full plastic moment before buckling, before any buckling can occur. So do not expect buckling to be the failure controlling mode. So which among the failure modes will control, not the local buckling, okay, in this area. Okay, this means what about on this next region? Okay, next region here, inelastic region, then elastic region. Take note of the value of nominal moment, 0.9 E kcx x divided by lambda squared. So this is the lambda region. Lambda R, which is the rupture, then lambda P, which is the plastic. Okay? So that's about the concept of the third failure mode. Okay? So let's go to the next one. The plastic or shear failure mode. Okay? So let's start again with the theory. So the next failure mode is according to strength, shear. So shear. So we are through with yield, flexure, lateral torsion, then local buckling, then now taking a look at shear. So shear strength, this means shear limit states for beams. So shear yielding of the web, failure by excessive deformation. Because shear buckling of the web means slender webs may buckle prior to yielding. So if the web buckle first before yielding, so this is now the controlling failure mode. But usually shear yielding, failure by excessive deformation. Okay. For shear stress, this is our strength of material or the theory of structure or the mechanics of deformable bodies. Shear stress is equal to VQ over IV. So Q is the first moment about the central axis. So we already know V, capital V, this is the total shear force. Then I and B, we already know about them. Then shear stresses generally are low in the flange area and they are concentrated in the web area because this is shear. And usually, shear does not control over the flexure. So usually, flexure control unless the length is short. So we have a short length beam. Then shear strength will control. Okay, so for design, simplifying assumptions are made like number 1, shear and moment stresses are independent. Number 2, web carries the entire shear force because flange shear are negligible. They have to resist against shear very small magnitude, very small, negligible. Shear stress is simply the average wave value. So let's just compute the average then. That is the shear, like this. Okay. So shear yield criteria. Yield defined by Mohr circle. Okay. So we already know the drawing of Mohr circle from physics and from theory of structure. Mohr circle. Also from mechanics of rigid bodies. Mechanics of deformable bodies, mechanics. So bond misses yield defined by maximum. So bond misses meaning this is the principle. There are several several models. This is one model defined by maximum distortion strain energy criteria. So applicable for ductile material. So these are the equations. This one and this one. So when we have what? Several rho 1, rho y, rho 2, then rho y and negative y. Okay? So for Fy is equal to constant for load direction, maximum shear is equal to or less than Fy over square root of 3 or 0.577 Fy. So usually we have what? 0.6 rather than this one. 0.577 or 0.6 Fy. This is usually used. Okay? In practice. So one misses failure criterion. I don't know the correct pronunciation of this. Bone misses or bone misses or bone misses. A failure criterion. Anyway, this is bone misses failure criterion for yield shear. With the average wave shear stress is equal to this 0.6 Fy. Okay? Therefore, we can find the total shear. So, 0.6 Fy times the area of the wave. So, do not need to include the area of the flange. Those are negligible. So, how? So, just like this. So, this one will cancel each other, but will be felt like this. So this is the proper convention of directional convention. So this one, as you can see, okay, the shear on an element, the element is the red portion, small element, so you can see, this one will cancel to this one will cancel this one in terms of moment, but this one will cancel to this one in terms of force, this one constitutes force. So 0, 0 equilibrium. Okay. So we have compression and tension. If we have this one, therefore we have what? Like this. Compression here and then tension here. Like this. You can take a look at it. These two will become one going out. These two will become one going out. These two will become one going in. So that's why we have this compression and tension component. Okay. So we have stiffener spacing A. So this one and this one. If there are no stiffener, so longer. The stiffener. So we have this one, potential buckling restrained by stiffeners. So these are the stiffeners. The red portion of the stiffeners. So being restrained. So if there are no stiffeners, so we have what? Potential buckling restrained by web slenderness only. So that is the only reason why this will not buckle. So when web is slender, it is more susceptible to web shear buckling. However, there is additional shear strength beyond when the web buckles. Web shear buckling is therefore not the final limit state. Okay? The strength of the truss mechanism controls the shear strength called tension field action. Okay, so there is tension field action. Tension can still be carried by the web. Okay, can still resist. Okay, can still resist like this, even though there is a buckling on that. Okay? Can still resist. So when the web is slender, it is more susceptible to web shear buckling. Okay, slender. So meaning we are in elastic region. However, this additional shear strength beyond when the web buckles. Web shear buckling is therefore not the final limit state. So compression can be carried by the stiffener. So this one. So it looks like what? It looks like a trusses. So it looks like a trusses. So like this. Truss element. Or compression element at this vertical red portion, then the green are the tension. Okay? And for field tension action to be effective, the truss forces must be resisted at its node point. Where are the node points? Here. These are the node points. There, this point, this point. So those are the node points. Okay? Therefore, end panels are not effective, nor are widely spaced stiffeners, nor panels that are not well restrained around their perimeter. So take a look. Okay, so that's the theory of shear. Let us take a look at the code. What suggestion the code will give us. So shear strength. So without tension field action, so nominal shear strength only is 0.6 Fy AWCV1. So equation D2-1. So 0.6 Fy, so we already know that is from bone misses failure criteria. Okay, so AW, that is area of web. CV1, that is reduction factor for shear buckling. Okay. So for again, those without tension field action, for a rolled I-shaped member, H over TW, if it is less than 2.24 square root of V over Fy, then phi shear is equal to 1. Meaning, omega is equal to 1.5 and CV1 is equal to 1. Okay? So, this is what will happen. because CV1 is equal to 1. So for all other I-shape members, so 5 shear is 0.9. So take a look. This is 1. Pi shear is equal to 1. Now pi shear is equal to 0.9 for all other I-shape members. Okay. For I-shape member which is rolled with H over TW less than 2.2 square root of V over Fy. Okay. So this is H over TW is equal to less than 1.1 square root of kV E over Fy. So again, it could be greater than 1.1 square root of kV. So we have what? Equation G2 dash 3, equation G2 dash 4. So now CB1 is 1.1 square root of kV E over Fy over H over TW. So we just divide this one with this one. Okay, so divided. So kV, what is kV? That we are talking about here. kV here, the factor, the modifying factor here. So kV is 5 plus 5 over quantity AH or A over S squared. Okay, so kV is equal to 5.34 if no stiffeners are present. If A over H is greater than 3. A is the clear distance between transverse stiffener. H is the clear distance between flanges. Okay, so that is our code provision for the strength. Okay. So just very fast, we will finish this faster. Now let's just take a look at very fast serviceability. So serviceability. This is not strength limit state but serviceability limit state. So serviceability limit state, we have deflection. So deflection, elastic behavior, limit set by project specification. Okay, how much we need to limit it. For example, L over 240, L over 360, L over 500. Okay, L over 1000. Okay, so we are familiar with L over 240, L over 360, but this one is L over 500, L over 1000. Okay, this is the first time. Okay. It is not, you cannot see this in timber and in reinforced concrete. So this is for steel. Okay. Deflection. So calculate deflection in beams from expected service dead load, then provide deformation in beam equal to percentage of dead load, deflection in opposite direction. It is important not to over camber. So we already know what do we mean by cambering or camber of the beam. The result is a straight beam after construction. Okay, specified on construction drawing. So cambering is usually used, okay, but that is what countermeasure against deflection. That is the reason why we do this, to counteract deflection. So beam without camber, okay. So results in deflection that looks like that. Okay. So beam with camber. As you can see, do you see beam without camber here? Without camber. This is the beam without camber. Okay. without camber. Now we have a beam with camber. Okay. So if the beam camber is on the maximum, we have what? It is straight now. So because of the camber. So maximum load, okay, we have now a straight line. That is our camber countermeasure against deflection. So now, what the code says about this serviceability limit. So let us look at the code. So we have the code here. Deflection. There are no serviceability requirement in IIEC. There is none. So there is no provision. L1 states limit shall be chosen with due regard to the intended function of the structure and shall be evaluated using appropriate load combinations for the serviceability limit state. Okay, so that means it is not a requirement because it is for service, so meaning the code only concerns itself with the safety, okay, rather than performance. Okay, so that is the concept of the code manual. Okay, any questions? So that's all about the theory, the code provisions, explanations. So I will just post examples on my own accord. I will record and post examples. So examples are the only thing we lack with regards to the discussion of beam. I will post the sample for analysis and design, and that's all for our semester. Why? Because we cannot take the final exam yesterday, today, and tomorrow, because we have 3 days of entrance exam in our university for applicants to become freshmen of our school. Take note, there are 7,000 applicants and only 2,000 will pass and become freshmen. Okay, so that's the reason why we cannot have a face-to-face final exam up to tomorrow. I will be an examiner tomorrow. So maybe I will post to schedule our final exam either Thursday, Friday, or Saturday. Either one of those. Because I will what? I will make the necessary arrangement to borrow the room for our final exam. Okay? Any question? Any question? There are no questions. Again, deflections and serviceability requirements are not to be found in IIEC manual. This is your professor, Dr. AP, preaching engineering for nation building. See you on the final exam, face-to-face. I will just make the necessary arrangement and post in our GC. Thank you.